So let's switch over to PowerPoint, making use of PowerPoint and LiveWire Virtual Laboratory, as we've done thus far in this video lecture series. Inside the text box for the title of the first concept we're looking at today, which is equivalent resistance. We're looking at the equivalent resistance of various configurations of resistor or resistor configurations, resistor arrangements. So equivalent resistance can also be called total resistance. So when I say equivalent resistance, I mean total resistance. So we'll be starting with total resistance of resistors connected in parallel. There are two major ways you can connect resistors. You either connect resistors in parallel or in series. So we'll start by connecting resistors in parallel. So let's switch over to live wire, passive components, resistor. There are other passive components apart from resistors, but for now we'll focus on resistors. So let's get out to resistors. So I want to show you how to connect two resistors in parallel. You click one terminal, click, drag, click. Okay, this is slightly misbehaving. Let me delete, click again, click, click, click. So you connect one end of one the terminal of one resistor to the other, like for like. So this is how to connect two resistors in parallel, and both resistors are 1 kilo ohm resistors connected in parallel. So you can adjust the positioning, but if you connect two resistors like for like, the terminals like for like, you have a parallel configuration. So this is how to connect two resistors in parallel. You connect one terminal of one resistor to the corresponding terminal of the second resistor. So let's get a power supply. If you want to connect a power supply to resistors in parallel, you drag a cell, you click one end, positive end of positive terminal of the power supply, DC power supply, connect a negative terminal of the DC power supply to the other end. So we've successfully connected a DC power supply to a parallel load or parallel connected loads. So two resistors are connected in parallel, and then they are powered by a DC supply of 1.5 volts. Let's shift it down a bit. Let's get output devices like a filament lamp. You can also, instead of using resistors as a load, you can use a lamp as a load too. Filament lamps also have their own resistance. So when I say load, it's not compulsory it always has to be a resistor. It can also be a filament lamp or a bulb, incandescent bulb. If you want to connect them in parallel, you connect it the same way I connected it to resistors in parallel. One terminal to the corresponding terminal of the other bulb or incandescent lamp. So let's connect power supply across the two filament bulbs connected in parallel. So let's simulate, and we see here that none of the bulbs came on because the voltage is way too low. If we double click or right click, you can change the properties. We can increase the voltage. Let's try 5.5 volts. Simulate. You can see here, I don't know if you can see, it got slightly brighter. There's a little yellow coloration there. Oh, okay, not kilovolts, too high. Let's try 10.5 volts. Let's simulate. Okay, it comes on. It's not bright enough as I want it to be. So the point here is that the more you increase the voltage across a load, the more current flows through the load, and the more current that flows through an incandescent bulb, the brighter the bulb will be. The same thing too goes for LEDs and other output components that give out some kind of output, whether visually in the form of lights or form of sound like a microphone. So let's look at another concept, calculating equivalent resistance of resistors connected in parallel. Now, when you connect resistors in parallel, you can actually we actually do that when we want to get another value of resistance that is different from the resistors that we are connecting in parallel. So you can calculate the total resistance when you connect two resistors or more than two resistors in parallel. You can calculate what the total resistance will be, and that is what we want to examine next. So if we have two resistors R1 and R2 connected in parallel, what is the total resistance? That is what we want to consider next. So let's delete the second circuit. Let's shift this up a bit or shift it down. R1 and R2 are in parallel. Each one of them is 1 kilo ohms in resistance. And let's insert a text box or an equation, because the formula for total resistance or equivalent resistance of parallel resistors, it's in a fraction, so we need to insert a fraction, the object holder for a fraction under equation in PowerPoint. So let's insert subscript. We need to insert subscript. Yeah, there it is. Not superscript but subscript. So 1 over RT, 1 over R subscript T. So this will signify, or this will represent our equivalent resistance. So wherever you see RT, it's RT signifies or will signify total resistance or equivalent resistance. Whenever you see that, that's what it means for this lecture. You see RT anywhere, that's total resistance or equivalent resistance. So I'm trying to generate a formula for parallel resistance, total resistance when you connect resistors in parallel. What's the total resistance? So 1 over RT, that is 1 over total resistance, equal to 1 over R1 plus 1 over R2. So that is exactly what I'm trying to do now. It's taking a while to generate this on PowerPoint. Plus, so this is the formula for resistors in parallel. If you have two resistors in parallel, this is the formula you use if you want to get total resistance. So 1 over RT, where RT is the total resistance, equal to 1 over R1, that's the first resistor in parallel, plus 1 over R2, which is the second resistor in parallel. So if you have two resistors in parallel, namely R1 and R2, you find the reciprocal and you add them together. That will give you 1 over RT, but not necessarily RT. Remember, we are looking for RT, not 1 over RT. 1 over RT is the reciprocal of the total resistance. We are looking for total resistance. That means after you solve 1 over R1 plus 1 over R2, you need to still change. You still need to find the reciprocal again of 1 over RT to become RT. I'll explain what I mean by that now. So RT is actually what we are looking for, not 1 over RT per se. So it means that we still need to change the 1 over RT back to RT. Me representing it in 1 over RT is just for easy remembrance. You can easily remember that 1 over RT equals to 1 over R1 plus 1 over R2. It's easier to remember that than to remember the actual formula for RT. So after solving for 1 over RT, you still need to find the reciprocal again to get RT. So 1 over R1 plus 1 over R2, we can actually simplify that using LCM. If you simplify 1 over R1 plus 1 over R2, you find the LCM. The LCM is R1, R2, and then you add them. This is O-level mathematics. I probably should not spend too much time explaining how it works. But this is the actual formula for RT. If you find the LCM of 1 over R1 plus 1 over R2, find the LCM, and then you, from the LCM, you simplify that the two separate fractions will become one single fraction. Then you find the reciprocal of that fraction, you get 1 over you get RT, what RT is. But just for the sake of illustration, let me do the intermediate step, the step that I went through before this one. I probably shouldn't, I don't need to, I probably should not be doing this. It's way lower than this level. There you are, but just for the sake of it. So the LCM of R1 and R2, we know it's R1 R2, just multiplying the denominators of both sides of both fractions. So, and then R1 R2 R2 gives you R2, and then R2 in R1 R2 gives you R1. So that's R1 plus R2 on the numerator and R1 R2 on the denominator. Then we find reciprocal, you get that. So that's the formula for total resistance or equivalent resistance of resistors in parallel. So let's go back to live wire and change the resistances to 1000 ohms. Actually, 1 kilo ohm is the same thing as 1000 ohms, but just for the sake of illustration, let's stick with 1000 ohms. It's still the same thing as 1 kilo ohms either way. So now, if I let me copy that image and paste it here. That's 1000 ohms, two 1000 ohm resistors connected in parallel. So if you connect 1000 ohms, two pieces of 1000 ohm resistors, if you connect them in parallel, what would be your total resistance? So that's what we want to do now, and we're going to use that formula. We have to write this formula we're going to make use of. So we make use of this formula. Remember that we got this formula by saying that 1 over RT equals to 1 over R1 plus 1 over R2. It was when we simplified that we got this formula. So it might not be easy for you to remember this formula, but at least if you remember 1 over R1 plus 1 over R2, you can easily simplify to get this. So let's replace R1 and R2. They are both 1000 ohms. So 1000 ohms multiplied by 1000 ohms at the numerator. Then the denominator, R1 is 1000 plus R2 is also 1000. So 1000 times 1000 numerator divided by 1000 plus 1000 at denominator. So whatever we get, whatever final answer, whatever figure we get from simplifying this expression or this equation will give us our total resistance. If you connect two resistors that are 1000 ohms each, if you connect them in parallel, that will be the equivalent resistance. That will be the total resistance. So let's do that. So we have 1000 multiplied by 1000 over 1000 plus 1000 equals to RT. So what is our RT? RT, total resistance, like I said before, or equivalent resistance. So let me do some arrangement here. RT. So if you simplify this, you actually get 500 ohms. The numerator is the numerator will give us 1 million, and the denominator give us 2000. So if you divide that with your calculator, you get 500. So if you connect to, what this means is that if you connect to 1000 ohm resistors, if you connect them in parallel, it's like as if you are connecting a single 500 ohms to the voltage source. So two 1000 ohm resistors is the same thing as one 500 ohm resistor. If you connect two 1000 ohm resistors in parallel, it's the same thing as having just one 500 ohm resistor. So that is the equivalent resistance of two 1000 ohm resistor is the same thing as a single 500 ohm resistor. So that is what we want to prove. So we've proven that already. We've proven that using the formula for equivalent resistance for parallel resistors or resistors connected in parallel. So let's try and prove it using. We can also prove it using live wire, rather, by using live wire environment, a virtual laboratory, we can also prove that this formula is right, this formula works. So let's get a 500 ohm resistor connected to terminals. We get terminals here. Connect this terminal to one end of the resistor. Click and drag like so. So this is a 500 ohm resistor. It's basically the same thing. We can get, if you don't have a 500 ohm resistor and you have two 1000 ohm resistors, if you connect those two 1000 ohm resistors, it's like you've replaced having a single 500 ohm resistor. So let's copy that and paste it inside PowerPoint. Click, expand it a bit. So if you have a circuit that needs a 500 ohm resistor and you don't have that, but you have two 1000 ohm resistors, you can connect those two 1000 ohm resistors and it will basically be equivalent to having one single 500 ohm resistor. So that is one of the good things about the parallel or the formula for determining resistance of resistors connected in parallel. So two 1000 ohm resistors in parallel is equal to one resistor, one 500 ohm resistor. So that is the usefulness of connecting one of the usefulness of connecting resistors in parallel is that you can get another value. You can get another value of resistance that would be probably useful for your circuit. So let's see. Proof. You can prove by a virtual experiment using the live wire virtual laboratory. You can also prove it. We can prove that they are the same. We have proven using the formula for parallel resistance. You've used that formula to prove that, or we've proven that that formula works, that formula is correct by giving a test case of two 1000 ohms resistor. But we can actually verify that by running an experiment. We can run a virtual experiment, and with that experiment we can see whether the formula actually works or not. So you can also just go to determination of resistance without ohm meter or color code. I'm sure you must have learned last semester how to determine the resistance of a resistor by checking the color code on the body of the resistor, or using an ohm meter. You can use a multimeter, set it to ohm meter range, and you just place the multimeter terminals on the across the resistor, and it will read out the resistance of the resistor. But for us to prove the parallel law or the parallel formula to be correct, we need to be able to determine resistance of a resistor without having an ohm meter with us, or without looking at the color code. So if for some reason there exists a resistor that doesn't have color code, or the color code has faded, we can use a voltmeter and an ammeter to determine the resistance of the resistor. So we want to determine the resistance of a resistor without an ohm meter and a voltmeter, without an ohm meter or the color code. And by doing that, we are going to prove that the formula for the equivalent resistance of resistors in parallel, you're going to prove that law is correct by running this little experiment. So let's get a power supply of about probably 10 volts. Let's make it 10 volts. So we are using a single cell DC power supply of 10 volts. Let's get an ammeter. Now we said we want to use an ammeter and a voltmeter to determine the resistance of a resistor, so we need an ammeter for that, definitely. So let's connect a voltmeter, an ammeter, to measure the current through. Remember we stated before that you measure current through and you measure voltage across a load. You measure current through a load and you measure voltage across a load. So we connected the ammeter so it will measure the current through the 500 ohm resistor, and we also need a voltmeter. You place the voltmeter to measure voltage across it, So we connect the voltmeter across the 500 ohm resistor. So we want to determine that, of course, from live wire we've seen that the resistance of the resistor is 500 ohms, but we want to confirm it. So let's simulate. Now there's an issue here. The values we are seeing of the current, that current value here, and the voltage value they were seeing, that is current value and the voltage value there, is actually not, it's lower than what it should be. We had this issue last towards the end of the last module, and I termed it due to there was a problem with the single cell battery, the internal resistance of the single cell battery. It has some internal resistance that's making the voltage to drop. So if I increase, okay, let's take it back to it's 10 volt. Yeah, so if we change, if I place a voltmeter directly across the battery, normally the voltmeter should give me 10 volts because this is a 10 volt power supply, and I now measure 10 volts. I measure usually this is 9.8 volts. This is 9.8. It should be the same thing, since I'm connecting a voltmeter across the battery or the single cell. So it means there's a problem with this cell. It means I can't use that cell for every resistor, so I need to change the model or the component to a battery. Now so the battery is more power, can deliver more power than the cell according to this virtual laboratory. This 1.5 volt cell, or the cell generally here model, is like the small cell that's in, or the small battery that you have in your wristwatch or your calculator. It cannot deliver much power. So that is what the cell model here is like, that cell. And whereas the battery model in live wire is like a standard battery, like a car battery. So you see that the battery contains multiple cells inside it. So now if I have a battery that's 10 volts, you see that it's reading exactly 10 volts here. So from now henceforth, we'll no longer be using a single cell to represent a battery. We actually use just a battery, an actual battery that is modeled after an actual battery, not a cell that's modeled after a small wristwatch battery. So let's delete that voltmeter. So now we can now continue with our experiment. So henceforth, we'll no longer be using the cell, we'll be using the battery. So now the current through the resistor is 20 milliamp, if I can see that correctly. It's and then the voltage across is 10 volts. So you just use I've written to right here that you use Ohm's law, V equals IR, and if you rearrange it, R equals to V over I. So R equals to 10 volts, which is the voltage, over 20 milliamps, which is the current. So 10 volts over 20 milliamps. 10 volts over, now 20 milliamps is something as 0.02 amperes. So if you do that, we have 500 ohms. So we see that with just a voltmeter and an ammeter, we can determine the resistance of a resistor. You will just apply Ohm's law, and then we get that stuff. So now to prove the parallel resistance formula using a virtual experiment, which is what we just did now, or what we're about to do now, we are going to create another circuit. We created another circuit to show that if I use two 1000 ohm resistors in parallel, it will give me the same result as if I use a single resistor of 500 ohms. So let's prove it. Let's prove that our parallel resistance formula works. So I probably need to shift this, probably shift it up or shift it down. So we want to, we've shown before, we tried to prove before that two 1000 resistors in parallel is something as one single 500 ohms. So let's use virtual laboratory live wire to verify this. So let's shift this up a bit so we can create more space to draw another circuit. So we need passive components, resistors, about 2 of them. Let's up the first one, click and drag the second one. So remember how to connect two resistors in parallel. This is, okay, let's call this one R3. Oh, okay, we already have R3. Let's call it R4 for now. Let's change this one to R2. Double click, change it to R2. Oh, we already have R2. R2 already exists. Cancel. Okay, yeah, this is R2. Okay, double click. Let's make this R1. then double click. Let's make this R2. So click one end of the resistor to the equivalent or the corresponding end or terminal of the other resistor. So this is how to connect resistors in parallel, the other end to the corresponding other end. So these resistors are both in parallel. Let's drag it a bit, drag it around. Power supply, battery, no longer we're no longer using cell anymore, using battery, because the battery can deliver more power. That is, as it's delivering the power, its voltage will not be dropping. But if you use a cell, if you connect a load to a cell that is much greater than it can handle, or that demands more current than it can deliver, the voltage will begin to drop. So you connect, as usual, the ammeter. You connect the ammeter to measure the current through the resistors that are connected in parallel, and then we connect the voltmeter across. And the voltmeter is connected across, automatically it's across both of them. As the way we connected this shows that it's across. We will come to that later, but this is how to connect voltmeter across resistors in parallel. We've connected ammeter. Let's shift this a bit. Click. Let's see if we can shift the wire. You can click, or delete, probably just delete it. Then we connect again. So we've connected the ammeter to measure the current through both resistors, and the voltmeter to measure voltage across both resistors connected in parallel. Remember that both resistors are 1000 ohm resistors each, although here is represented as 1K. So let's duplicate it. Highlight, copy and paste, and let's click, delete. Now I want to show you this another way we can connect this. We can connect this in parallel as this, as so. Connect this already in parallel as so, and then I'll take one end, just a little one end here, click and connect, then click and connect. It's the same thing. This is another way of connecting a voltmeter across two resistors in parallel. It's basically the same thing. The two, if I click on simulate, you see here that the values are the same. So let me shift the voltmeters back a bit so that I'll be able to see the voltmeter values. Simulate again. Now we see that the voltage across is 10 volt and the current through is 20 milliamps for both, for the middle and the bottom circuit. So they are basically the same thing. So there are two options of connecting, or two ways you can connect resistors in parallel, or rather connect the voltmeter to two resistors that are already connected in parallel. So let me change the resistance to 1000 ohms. Remember that 1000 ohms is taken as 1K. I just want for generalizer, let's work with ohms instead of kilo ohms. So 1000, remove the K, double click, 1000, remove the K, just press down, remove the K. Okay. So let's simulate again. The current through all three resistors is the same thing, 20, all three circuits rather the same thing, 20 milliamps, and then the voltage across all three circuits, they are the same thing. So it means that if I use a single 500 ohm resistor, it's basically the same thing as connecting to 1000 resistors in parallel. So if I use Ohm's law formula of R equals to V over I, the V is 10 volts and the I is 0.02 amps. So I've proven that two resistors in parallel equal to 1000 resistors in parallel equal to one resistor, one 500 ohm resistor. So equivalent resistance of three resistors in parallel. Now we've done that for two. What we did just now, at least so far, is checking the or obtaining the equivalent resistance of two resistors connected in parallel. So what about three resistors connected in parallel? We go back to initial formula. Let's first delete. Let's delete all this circuit, or at least these two, and delete. So remember that formula for two resistors in parallel, which was 1 over RT equal to 1 over R1 plus 1 over R2. If it's three resistors, we just add one more, so it will be 1 over R1 plus 1 over R2 plus 1 over R3. And if you simplify that, the LCM of R1, R2, R3 is, of course, just R1, R2, R3, like that, just multiplying them together. So O-level mathematics, you should be able to obtain that. So let's go to here and left right now. We've connected R1 and R2 in parallel. Click R2, connect it to R3 in parallel. So this is how to connect three resistors in parallel, R1, R2 and R3. They're connected in parallel. one end to the corresponding end of the other, from that end to the corresponding end of the other. Pretty easy. So 1 over R1 plus 1 over R2 plus 1 over R3. This is R1, this is R2, this is R3. Then the next step, 1 over RT, which is where RT is the total resistance. Then the LCM R1, R2, R3. Then R1, R2, R1 in R1, R1 in R1, R2, R3 gives us R2, R3. Then plus R2 in R1, R2, R3 gives us R1, R3. Then R3 in R1, R2, R3 gives us R1, R2. So that's very basic actually. Equal to 1 over RT, but it's RT we actually need, not 1 over RT. So we need to flip the fractions on its head, flip it upside down, and then R1, R2, R3 goes up, where the former numerator now becomes the new denominator. The old denominator becomes the new numerator. I hope you understand what I mean by that. So now all three connected in parallel. So let's change the resistances from 1000 or from 1k. Let's make it 900 ohms for each resistor. Let's remove the k. Okay, double click. 900, remove the k. Okay, double click. 900, remove the k. Down. Okay, so we are going to want to connect 3 900 ohms in parallel, and then that's our formula. We've obtained that formula before. We substitute the values. R1 is 900, R2 is 900, R3 is 900. If you substitute those values and use your calculator, you will get 300 ohms. So if you connect 3 900 ohms in parallel, it's the equivalent resistance is 300 ohms. So it's like having one single 300 ohms if you connect three 900 ohms in parallel. So let's do we are done with parallel configuration. So equivalent resistance of resistors in series is what we want to do next. So if you have R1 and R2 as usual in series, this is how to connect in series. Just click them, you place them side by side, you connect one end to the other, and the other two ends are free. So this is R1 and R2 in series. So I hope you're able to distinguish between series and parallel connection. This is series connection. So we are connecting them on a straight line from one end to the other. The other two ends are free, at least for now, till you connect. So if you want to add power, we want to connect a voltage supply across two resistors in series. Let's do that. You place it somewhere around here. Then you connect one of the free ends of the resistors in series to the positive terminal of the battery. Click, and you connect the negative terminal to the other end of the two resistors in series. Click. So you successfully connected two resistors in series to a voltage supply, and this is the formula. The formula for connecting resistors in series is different from that of connecting resistors in parallel. So RT, which is equivalent to total resistance, is R1 plus R2. It's not reciprocal, there's no fraction anywhere. So series resistance or resistors in series, the formula for resistance in series is quite straightforward. It's just addition, straight away addition. So R1 plus R2, that's all. If your resistors are connected in series and you want to get the total resistance or equivalent resistance, just add them together. Just add the resistances of each resistors together. So RT equals to R1 plus R2. Pretty straightforward on account of parallel resistance, or parallel resistors rather. So equivalent resistance of connecting two resistors of two resistors in series. Sorry about that. Wrong spelling. Oh no. Wrong. So let's go for equivalent resistance of three resistors in series. So if I add a third resistor R3, I rotate it, connect it to R2. I can move this. Let me highlight all three of them, copy and paste. So this is three resistors in series. So I hope you're able to distinguish between series, how to connect resistors in series and connect resistors in parallel. So these are three resistors connected in series. Remember, one end to the other end, and just like a bridge connect, just like having a bridge connection. So the formula, of course, is just R1 plus R2 plus R3. So if you have three resistors in series, just add them together. Add the resistances together. That's how you get the total resistance or the equivalent resistance. So RT is R1 plus R2 plus R3, just like that. And if there are four resistors, it will be R1 plus R2 plus R3 plus R4. So series resistance or series resistors are easy to it's easy to obtain this equivalent resistance or total resistance of resistors in series. So connect the positive to one end, and then the other end, the last terminal of R3, connect it to the negative terminal. So this is how to connect a voltage supply across three resistors in series. So let's move this. We deleted the other circuit, we don't need it. Move it up, copy and paste. You want to duplicate it. Now I want to show you that there are many ways you can connect three resistors in series. This is one way of doing it. I'll show you another way you can do it. You can move, I can rotate the third one. Let me delete the intersection, delete, click, rotate to the right. Now I can rotate one of the resistors like this, rotate it and still connect it this way. And then from here, complete the circuit, connect the end to the negative terminal of the battery. Now this is still the same thing as this one. These two circuits are basically, they are both connected in series. So you can either keep all of them on a straight line, or you can have one rotated this way. It's still basically the same thing. Copy and paste. There's one third way you can do it, and that way you can connect all three resistors in series and still be the same thing. Let me delete this. So I click delete this cable, delete this wire, rotate once again to the right, drag it down here, delete this wire, click, rotate to the right, and drag it down, and then click and drag, click, connect, click, drag, click, connect. So basically all three circuits are the same thing. They are all in series. 1, 2, 3 are all in series, regardless of the way the orientation. They are all the same thing, because it's one end of one to the end of the other. It's like the positive of one, although resistors don't have terminals, but they're positive and they are all the same. Now if I come here, this is 10 volts 3.3 milliamps. That is what the voltage supply is, the power supply is giving. It's the same thing, 10 volts 3.3 milliamps. So for all three circuits, it's basically the same thing. The power supplied by the voltage source is the same thing. It's 10 volts 3.3 milliamps. So all three circuits are the same thing. Either of these three is a good way of representing three resistors in series. You either connect them on a straight line, or you have one rotated a bit, or you can connect it the way the third circuit has been connected. So all three are connected in series. So let me do the first two. I think I'll work with the third one for now. So all three in this circuit, all three R7, R8, and R10 or whatever, they are all connected in series. So let's use if the first one is 400 ohms and the second resistor is maybe 250, should make it 250 ohms. Remove the K, okay. And the third resistor is 350 ohms. Remove the K, okay. So we have three resistors in series, one 400 ohms, one 250, and one 350 ohms in series. So you connect a battery, a DC voltage source of 10 volts across three resistors in series. Let's make the first resistor R1, just for labeling sake. The second resistor R2, and the third resistor R3, just for the sake of labeling. It has no effect on the calculation or the equivalent resistance. So three resistors in series. We could have connected this either of the other two ways, but let's just stick with this one for aesthetic reasons, basically. So let me highlight this, copy and paste. I brought the image into PowerPoint, drag it into PowerPoint, and remember that the formula for equivalent resistance of resistors in series is R1 plus R2 plus R3. Let's see if you can copy that formula, copy the formula and paste, click and drag, Okay, we have it there. RT equal to, copy, paste, RT, double click, space, equal to 1. And what is R1? R1 is 400 ohms, if I'm right, plus R2 is 250 ohms, plus R3 is 350 ohms. So we want to get the total resistance or the equivalent resistance of the two resistors in series. Let's get a calculator out to do additions and the likes. Calculator, 400, it should be like 1,000, if I'm right. 400 plus 250 plus 350 should be 1,000. Yeah, so that's 1,000 ohms. So if you connect these three resistors in series, it's the same thing as having one single 1,000 ohm resistor. So the equivalent resistance of the three resistors in series is 1,000 ohms. Let's get the symbol out. Capital letter omega, Greek character, that's omega. So the three resistors connected in series, 400 ohms, 250 ohms, and 350 ohms, it's equal to 1,000 ohm. So all three resistors connected in series is the same thing as having one single resistor that's 1,000 ohms in resistance. So let's go. This is 1,000 ohms resistor. Let's connect our 10 volts battery, our DC source. Let's connect it across the resistor and see if the voltage across the resistor and the current through, if it will be the same as when we have three resistors connected in series. So let me rotate that. Let me rotate it this way. This is another way of connecting resistor across a voltage source, or a voltage source across a resistor. As long as the terminals are connected right, the orientation doesn't matter whether it is vertical or horizontal. As long as the right terminals are connected to the right terminals, that's what matters. The orientation doesn't matter. It's just for the right terminals to be connected to each other. So we get the resistor and the battery, copy, paste, drag, click. So let me change orientation to vertical. I want to show you that whether you have the orientation as vertical or horizontal, it doesn't matter. The result will be the same. The right terminals are connected to the right terminal. If you compare the middle circuit and the third circuit, the second and third circuit, you see that the terminals connected to each other are the same. The terminals of both are the same, but the orientation of the resistor is different. But the right terminals are connected to the right terminals. So if I place my cursor here, this 10 volts, 10 milliamps, 10 volts, 10 milliamps, 10 volts, 10 milliamps, if I'm right. So it means that all three circuits are the same. They have the result is the same. They are drawing the same power from the battery or from the DC voltage source because they are the same. The three resistors connected in series is equal to or the same thing as that single resistor of 1,000 ohms, where that resistor has an horizontal orientation or a vertical orientation. As long as the right terminals are connected to the right terminals of the battery, it's all the same. It's all the same. So I hope you've been able to grasp the concept of having resistors in series and connecting resistors in parallel, how they differ from each other, and why we do that. Why do we have to connect resistors in series, and why do we have to connect them in parallel? We do that to get other values of resistances. That if you're looking for a 1,000 ohm resistor and you don't have it, but you have a 1,400, 1,250, and 1,350 ohm resistor, you can combine them in series to generate a 1,000 ohm resistor, and you use it in your circuit like that. So that's why we connect resistors in series and parallel. So now to prove the series resistance formula using virtual experiments. So we did that when we are looking at parallel resistors. So we want to prove the formula, that if we want to prove that the formula is right, we've proven that the formula for the parallel resistance or equivalent resistance of parallel resistors, we've proven that that formula works by running a virtual experiment in live wire virtual laboratory. So we want to do the same thing for the series formula, the formula that relates or that helps us to determine the equivalent resistance of resistors that are connected in series. So and we've said that connecting a 400 ohm, a 300 ohm, sorry, a 350 ohm and a 250 ohm resistor in series is equivalent to just one 1000 ohm resistor. So let's verify that. Remember from Ohm's law that V equals IR. If you make R the subject of formula, then R equals to V over I. That's from Ohm's law. We've gone over this over and over again, so it probably should have stuck in your minds by now. R equals to V over I. So all we need is a voltmeter to give us a voltage reading, and we need an ammeter to give us the current reading. So the voltmeter will help us with the value of V, and an ammeter will help us with the value of I. So we did this when we are trying to prove the formula for parallel resistors or parallel resistance. Let's first connect an ammeter to measure current through this 1000 ohm resistor, and a voltmeter to measure the voltage across the 1000 ohm resistor. So click let me drag this down a bit, click, drag down a bit, click, drag down a bit, click. Okay, this is misbehaving a bit. Click, drag, click, click. So click, 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 click. Okay, so we've connected the voltmeter across the 1000 ohm resistor, and so we see that the current is 10 milliamps and the voltage is 10 volts. The voltage across the load is 10 volts as determined by the voltmeter, 10 volts. So our V is 10, backspace 10 volts, and then our I is the current flowing through that 1000 ohm resistor, which is 10 milliamps. So that will be 10 milliamps is equal to 0.01 amps or amperes. Let's get our arrow in just to show that we went from this step to this step. The formula step, R equals to V over I, to the substitution step of substituting 10 volts for V and 0.01 amps for I. So 10 divided by 0.01 is 1000. So that means R equal to 1000 ohms. So we've used Ohm's law to verify, in conjunction with the live wire virtual laboratory, to verify the value of that resistor. We used a voltmeter and an ammeter to verify that the value of that resistor is 1000 ohm. In conjunction, or it was a collaboration, so to speak, between Ohm's law and live wire virtual laboratory. So we verify that value, the 1000 ohm value of resistance of that particular resistor, we verified it using Ohm's law. So copy and paste. So we are depicting that we used this circuit to generate or we applied Ohm's law as shown on the right. We applied it to the circuit diagram to the left. So R equals to V over I. Here V is 10 volts and I is 0.01 amps. So let's go back to live wire, and we can do the same thing for the other circuits, R1, R2, R3. Copy and paste. Let me drag this down a bit for more space, and drag this up a bit. Click, drag this, rotate. Okay, let me go back to the original configuration of 3 resistors in series. Remember that I've not made any change. It's actually still the same thing. This connection and the one on top, they are all the same. Let me drag the symbol R7 and the 350 ohms. Let me drag the labeling rather. Let me drag it down a bit. So this middle circuit is still the same thing as the top circuit. They both have 3 resistors connected in series, even though their orientations are different. Because if you compare the two, the terminals are the same, the terminal connections are the same, just that their orientations are different, but the terminal connections are very much the same. And that is what matters most in a circuit. It's connecting the right terminals. It's not just about the orientation, whether a component like a resistor is horizontal or is vertical. If the right terminals are connected, that is what matters. So now I want to measure voltage across these 3 resistors. Now I'm going to do something that probably I've not done before. Now look at this. Connect it from one end of the series resistors to the other end of the series resistors. So this is how to connect a voltmeter across 3 resistors in series. So from there I tap from a cable or a wire from on the end terminal to the battery. So now I've connected that voltmeter across the 3 resistors in series. At the same time, the voltmeter or the ammeter to measure the current through the 3 resistors in series. So we see here that the current through them is 10 milliamps and the voltage across them is 10 volts. The current is 10 milliamps and the voltage is 10 volts. So let me see, copy and paste. Let me see if I can I fit this into the slide? I'm not quite sure. Probably I need to let me duplicate. I can duplicate the slide, move this to a new slide, copy, and new slide, paste, drag this up. For illustration purposes, so that I can do a direct comparison. So copy and okay, let me go back to live wire to copy the circuit. Right click, copy and paste. So so you can see here that we've connected a voltmeter across the 3 resistors in series and an ammeter to measure current through them. So we use the same formula, R equals to V over I, which is obtained from Ohm's law. R equals V over I. Copy and paste. And, let me move this circuit. Move the circuit to a good position. R equals to V over I. Now we see here that it's basically the same thing, because if we simulate, the voltage is 10 volts. R that's equals to 10 volts. V is 10 volts. Current I is 10 milliamps, which is equal to 0.01 amps. So if we resolve that, we get 1000 ohms. So it means that we've proven that all 3 resistors connected in series is equal to a single 1000 ohm resistor. We've proven it using live wire. and also prove that the formula works. So please note how we connected the voltmeter across all 3 resistors in series, and then we use the formula to verify. So we are done with verification of the Ohm's law using live wire. So now we go to we examine the voltage across individual resistors in a parallel configuration or in a parallel arrangement. Parallel configuration. Let's adjust the title to the center, align to the center, zoom out a bit. Let me adjust that, zoom in back a bit. So we are going to now examine what the voltage is across each resistor in a parallel configuration. So if you connect resistors in parallel, what will be the voltage across each resistor? So let's get rid of all the circuits we've drawn so far. Get rid of them. Start afresh, a blank slate. We start, of course, as usual, passive components. Get our resistors. Resistor 1. Let's make it 500 ohms. Resistor 2. Double click. Let's change the resistance to remove the K. 1000 ohms should work. Resistor 3. 2000 ohms. Okay. So we have 3 resistors in parallel. One is 1000 ohms, the other is 500, and the last one is 2000 ohms. So 3 resistors in parallel and the resistances of the resistors have different values. We're connecting them in parallel. We want to determine what the individual voltage, how to determine the voltage across each individual resistor. So let's get our power supply, battery as usual. Connect our battery on one end. So we're going to connect the battery across all 3 resistors in parallel. Then we're going to try and determine what the voltages will be across each individual resistors. So let's connect in parallel, one end to the corresponding end, second terminal to the corresponding second terminal. Why is misbehaving? Click, 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 and click. So click on that junction, click, click, delete, click again, click, and click, and click. So connect the 3 resistors in parallel, connect them across the voltage supply of the battery. Double click, let's change the value to 10 volts. Okay. So we've successfully connected our battery across 3 resistors in parallel. Let's get our voltmeter. Remember, we want to measure voltage across each individual resistor, so we need the voltmeter for that. Rather, we need 3 voltmeters. Each voltmeter would measure the voltage across each resistor. So since you want to measure the voltage across 3 resistors, we need 3. So we can connect it this way. We connect that voltmeter across that resistor that way, this end to this end, this end to the corresponding end. So we see that the voltmeter is across R1 and that voltmeter is across R2. Let's get the 3rd voltmeter to connect across R3. Click on this end, one end, the same end on the resistor from this end. Click from this end to the corresponding end in R3. So we connected 3 voltmeters across 3 individual resistors. So each resistor has its own voltmeter. So let's simulate. Let's see the value. Now see that the value there is 10 volts, 10 volts, and 10 volts. So what this means is that regardless of the value of the resistance regardless of the value of the resistance value of each resistor, if you connect them in parallel, they're going to have exactly the same voltage. So this brings us to an hypothesis that the voltage across resistors connected in parallel is the same, regardless of the value of the resistance. So even though one resistor is 500 ohms, the other one is 1000, the other one is 2000 ohms, the voltages across all three was exactly the same thing. Was the same as the voltage supplied to the circuits by or from the voltage source on the voltage supply, the DC voltage supply. So note, voltages across resistors that are connected in parallel are the same. Are the same. So if you connect resistors in parallel, the voltages across all those resistors in parallel, regardless of the value of their resistances, the voltages across them is exactly the same. So we've used live wire to prove that this hypothesis is right. So we connected three resistors in parallel, gave each one of them their own voltmeters, and then we powered it with a 10 volts battery. We discovered that the voltages across each of these resistors were the same. They were all 10 volt, 10 volt, 10 volt across all three resistors. Even though their resistances were the same, the voltages across them were the same. You can connect voltage across it in another way. What if I connect it like this? The top instead of direct is basically the same thing. If I connect it like this, delete this one, click and delete, click and delete. This is another way of connecting voltmeter across the load. Click and delete, click, drag, drop. This is another configuration, another way. It should give us the same result because there's nothing in between. It's basically the same thing. If I connected it closer to the resistor or farther away, as long as there's no resistor, there's nothing between the former place I connected and the new place, the new connection point. If there's nothing between, it's basically as if it's still the same thing. It's only if there's something between, like another resistor, that's the connection can be wrong. But this is the same thing. The two circuits are the same. See, 10 volts across, 10 volt across, 10 volts across. So 10 volt across, 10 volt, 10 volt. So the two circuits are the same thing because the former connection point and the new connection point, there's nothing. If you have no load between, if you have nothing else between the two connection points, the two connection points are valid. They are the same as long as there's nothing between them. Now, if I change the source to 25 volts, you see here that the voltage has dropped to 24.98. It means that this battery is already at its limit. So it means that 25 volts is too high for this battery to supply. Let's make it 5 volts. 5 volts is something more valid. So 5 volts. So if I connect 5 volts across and then 5 volts, let's change the other pass voltage supply. This is voltage supply to 5 volts. So simulate. If I connect 5 volts across all three resistors, the value still will be 5 volts. So the voltages across resistors in parallel is determined by the voltage supply. So it's all the same basically, regardless of the value of the resistances of the resistors connected in parallel. The voltage you apply to them will be the same as long as they're in parallel. So we are done with that. We have proven that resistors connected in parallel, they have the same voltages. So examining the individual or the current through individual resistors in parallel. So we have proven that the voltages across resistors connected in parallel, we've proven that the voltages are the same. What about the current? Is the current going to be the same? No, it won't be the same. So let's prove that the current will be, even though the voltages are the same for resistors connected in parallel, the current will be the same. But we can determine what the current values will be. So let's get on that. So we are examining the current through individual resistors for resistors connected in parallel. We want to now check what the current will be. The voltages are the same if you connect resistors in parallel. the voltages across all the resistors connected in parallel will be the same, but the current won't be the same. Let's prove that, and let's see how you determine the current through resistors, individual resistors that are connected in parallel. So let's delete the voltmeters. This time, since it's current you want to measure, we don't need voltmeters for that. We need ammeter. We need ammeter to measure current. So let's get rid of the connections. Drag this resistor closer, drag it closer, and let's drag it closer. Let's drag it down, drag the resistors down to create space for the ammeter. I want to draft in 3 ammeters. When we wanted to determine the voltages of individual resistors, we needed 3 voltmeters to determine the voltage of each resistor of each of the resistors that are connected in parallel. We needed 3 voltmeters. Now that we want to determine the current of the individual resistors, we need 3 ammeters. So the first ammeter we connect through. Now note where I connected the ammeter to. It's directly connected to the resistor, so we are measuring the current through that resistor. Second ammeter to measure current through this particular resistor alone, and then we have to delete this wire. Click and delete the wire, then get in the ammeter this way, click, connect, click, and then connect. So we have 3 ammeters that will measure the current through 3 individual resistors. Now we are going to get a fourth ammeter that will measure the total current, the current that is coming directly from the voltage source, from the battery. So the fourth ammeter will take care of that. So let's return the battery voltage to 10 volts. So we have 3 resistors connected in parallel, and then we have ammeters that are connected to them in series to measure the current through each of the resistors, and then 1/4 ammeter that will measure the total current that is being supplied by the battery, the DC voltage source. So we want to measure the current through each resistor in a parallel configuration. There are 3 resistors connected in parallel. We have said before, we've proven the hypothesis that the voltages across each of the resistors connected in parallel is the same. As long as they're connected in parallel, they are going to have the same voltage. But we have a new hypothesis now that the current through them is not the same. Even though the voltages across the 3 resistors in parallel, or even if it's 4 resistors in parallel, if you have 1,000 resistors in parallel, they're going to have exactly the same voltage across all of them. So let's copy and paste. We want to prove in our new hypothesis that says that for resistors connected in parallel, the current through each and every one of them is not the same. It will depend on the resistances of each of the resistors. So let's decorate this with some arrows. Let's put an arrow here. Now this arrow shows that remember that current comes out from the positive and goes into the negative terminal of the battery. So that is from the original source of the battery. The current comes out, and then this is down direction. That it splits into 2. The current goes through the 3 resistors in parallel. That's why we have this directional arrows are facing down. Now when this current that's coming in this direction gets to this node or this junction, it splits into 2. It starts by coming, it comes out from the battery, the current comes out from the battery, it gets to this node, and then it splits into 2. It gets to this also, and also split into 2. So every junction it gets to, it splits into 2. One goes down into the resistor, the other one keeps going forward. And when that one that's going forward gets to another junction, part of it splits and goes down into the resistor, while the other one keeps going forward. So I'm showing you the direction of current, how current moves from the battery. It gets to the first junction, part of it goes down into the resistor, through the resistor, the other one keeps going forward, part of it branches and goes down into the second resistor, the other one keeps going forward, and then it gets to the last branch and goes down into the resistor. So let's call this current, the current coming from the battery, directly from the battery, let's call it IT. That's I total, I for current, T for total. So total current, we call it IT. So the total current coming out from the battery or from the DC voltage source, we call it battery. Let's change the font to Times New Roman so that we can see the IT very well. IT is the current. IT current. IT I and T. That's total current. So the total current that is being supplied by the voltage source is IT. So IT comes out from the battery. Now when it gets here to the first intersection, it branches into two. Now it branches into two. One part is I2. I2 flows through the first resistor there, I2, and then the second resistor, let's call the current going through the first resistor as I2. The second resistor, let's call it I3. I3 is the current that flows through the second resistor. And then the last one, let's call it I4. Let's call it I4. I2, I3, I4. So when IT branched into two currents, one was I2, the second one, the part that continued going forward will be I3, or rather, yeah, let me get this right. Let me move it to the right position. I3 plus I4. So now the current IT got to the first junction and branched into two. The first part that broke off from IT was I2. So I2 came out from IT. IT is the total current. It got to the first junction. I2 came out of it. The remaining part, I3 plus I4, continued going forward. And when it got to the second branch or the second junction, okay, let me change it first. This R2, this should be R3. Let's make the right nomenclature. R3. So the resistors are R2, R3, and R4. Let me copy. Let's make this one V for voltage, V1. Okay, so let's copy. So I'll be replacing the old image with a new image. Before we had the nomenclature on the resistors, we are wrong or we are inadequate. Let's get it right so that the current flowing to R2 will be I2. So we are matching the current to the resistors. Let's get that right. R2 IT I2, the current flowing through R2 is I2, the current flowing through R3 is I3, the current flowing through R4 is I4. So the currents and the resistors, they match, their nomenclature match now. I2 flows through, and then the last arrow that we've not named yet should be I4. We can make it actually it should be superscript or subscript rather. The 4 in front of the I's, or the 2, the 3, the 4 should be subscripts, but to save time, just write it as I2. We could have written it as I2 actually, as small 2. It should be subscript, should be small 2, but for the sake of time, probably this would have been faster if probably you had a writing tablet or a PC with a digital touch screen. But we may do what we have. So now I2 from Ohm's law, we know that V equals IR. If you make I the subject of formula, you can have I equals to V over R. So if we start from I2, for example, now I2 will be V2 over R2. So the V is not just any other V, it is specifically V2, and the R is not just any R, it is specifically R2. So for I2, the V across it will be V2, and the R, the resistance of that particular resistor, will be R2. So I2 equal to V2 over R2, where V is the voltage across R2 and R2 is the resistance of resistor R2. And remember that the voltages across resistors connected in parallel are the same. So that means V2 equal to V3 equal to V4 equal to 10 volts. That means V2 equals to 10 volts. We've proven already that voltages across resistors in parallel is the same. Now R2 is equal to 500 ohms. R2 is equal to 500 ohms. So that means R2 is 500 ohms. The resistance of the first resistor is 500 ohms, and the voltage across it is 10 volts because it's in parallel with a voltage source that is 10 volts. So that's, if we divide it out, that means I2 equal to 0.02 amps. 0.02 amps. 0.2 amps. That's I2. I2 equals to 0.02 amps. Let's copy and paste. You can do that for I3. I3, like I said, the number in front of the I should be subscript. If I had numbers like V3 and V2 and R3 should be all subscript, but for the sake of time, let's just leave them in their normal shape. So R2 is 1000, R3 is 1000 ohms. That will be 10 volts divided by 1000 ohms, which is 0.01 amps. 0.01 amps. That's I3, not I2 actually. Copy and paste. I4 equal to V4 divided by R4. R4 is 2000 ohms. V4 still remains 10. Remember that the voltage across resistors in parallel is the same. The voltage is the same because they are connected in parallel. We've proven that. So 10 divided by 2000 ohms, which is 0.005. So I4 is 0.005 amps. So yeah, we're done with that. If you run the simulation, let's see if it will be the same thing. Now we have done that with IT. Like I tried to explain before, IT comes out from the battery. It branches into two. It branches into I2 on one end, the other end is I3 plus I4. When I3 plus I4 gets to another junction, it's split into two. I3 comes out and I4 continues till it gets to the last resistor. So let's see, what is IT? Now IT is equal to I2 plus I3 plus I4. Remember that IT, total current, branched into two in the first place. When it got to the first junction, it branched into two. One part of the current became I2 and went into R2. The second part of the current was I3 plus I4, which eventually branched into I3 later on and I4 later on. So that means that IT, total current, is equal to the sum of the individual currents. So IT equals to I2 plus I3 plus I4. I2 is 0.02, I3 is 0.01, and I4 is 0.005 amps. So if you add them together, let's get a calculator already. 0.02 plus 0.01 plus 0.005 equal to 0.035. 0 equal to 0.035 amperes. So this is the total current. This is the total current that is supplied by the battery or by the DC voltage source. So that's 0.035 splitted into, okay, let's run the simulation to verify. When we run the simulation, we see that I4 is 5 milliamps. 5 milliamps is 0.05. So this is correct. Now 10 milliamps is same as 0.01 amps. I2 is correct, or I3 is correct, then I2 is 19.99 milliamps, which is same as 20 milliamps. It's same as 0.02 amps. So, and then the total current is 34.99 milliamps, which is same as 35 milliamps. And 35 milliamps is 0.035 amps. So we've used virtual laboratory, we've used live wire to prove that our calculation is right. So that this current here, the current in this branch is 14.99, which is approximately 15 milliamps. So if you had I3 and I4 together, 0.01 plus 0.05, that's 0.015. This is 15 milliamps. It's the same thing. This is 15 milliamps, approximately 15. This is approximately 15 milliamps of current here. That's 14.99 milliamps, approximately 15 milliamps. And this is 5 milliamps here. This is also 5 milliamps here, which proves that I4 is 5 milliamps or 0.05 amps. So our calculation is right. We verified our calculation through live wire virtual laboratory. So we've proven that the current through resistors in series, if you connect resistors in parallel, if you connect resistors in parallel, the current through them is not the same, but the voltage across them is the same. The voltages of individual resistors connected in parallel is the same, but the current through them is not the same. The current through them is determined by the value of the resistors, of the individual resistances, or the individual resistances of the individual resistor, or the resistances of the individual resistor. That's what determines the current through each of the resistors. But the voltages across the resistors are the same as long as they're connected in parallel. So confirming the value of total current by evaluating equivalent resistance. So now we got our total current IT. In this instance, we got it by adding the individual currents. We got it by adding the individual current of the individual current through each resistor. But there's another way we could have gotten the total current, and we're going to examine that now. Now we can get the total current by first getting the total resistance of the circuit. So with that, we'll be branching into. Alright, we've done this before. When we are, this is the formula for total resistance of resistors in parallel. We've done this before, so we are going to make use of this again. So let's just copy. Let's see if we can copy the formula. I think this formula will be better than, or we can copy either of them. So we copy these two. The formula for resistors connected in parallel. So if you get the total resistance of the three resistors connected in parallel, we can use that total resistance to get the total current. So we have 1 over R1 plus 1 over R2 plus 1 over R3. We've examined this before. But in this case, we have R2, R3, and R4. Actually, we changed the nomenclature, we changed the labeling. We didn't start from R1, we started from R2, R3, R2, R3, R4. R2 plus R3 plus R4. R2 plus R3 plus R4. This formula probably won't hold. It will be R. Let me see. What do we do with this? Okay, this is probably let's drag this down a bit. You copy and paste. Let's duplicate. Yeah, okay, that's too many duplicates. Ctrl Z. So let's get the duplicate and do it step by step. So what is R2? R2 is 500 ohms. R2 is 500 ohms. R2 is 500 ohms. R3 is 1000 ohms. R3 is 1000 ohms. So you have the option of, first of all, simplifying 1 over R2 plus 1 over R3 plus 1 over R4, simplifying it and then inserting the values, or you insert the values directly and then you now simplify. So R4 is 2000 ohms, R3 is 1000 ohms, and R2 is 500 ohms. So let's go. The LCM of 500, 1000 and 2000 is actually 2000. 2000 is the LCM of all three. That's 2000. So 500 and 2000 should be 4. 500 can go in 2000 4 times. Multiply by the one on top, that's 4. 1000 can go in 2000 twice, that's 2. Multiply by 1, that numerator, which is 2. And 2000 can go in 2000 just once. Multiply by 1, that is the 1. So this is secondary school mathematics, really. You should not struggle with this. So this means that 1 over RT, that is 1 over total resistance, it should be 7 over 2000. If you add 4 plus 2 plus 1 together, add 4, 2 and 1 together, that should be 7 over 2000. But that is not our total resistance. It's just the reciprocal of the total resistance, right? This 1 over total resistance is 7 over 2000. To get the actual total resistance, we need to flip the fraction on its head. Flip it over, turn it on its head, make the numerator the denominator, and make the denominator the numerator. So if you flip it on its head, you can get RT, copy, paste RT. So RT will now be equal to, the top will now be 2000 and the denominator will now be 7. So that's 2000 over 7. That is total resistance. So the total resistance of the 3 resistors connected in parallel is 2000 over 7 ohms. That's total resistance. So remember that what we're actually looking for is IT, total current. We got total current initially. We got it by adding the individual currents through each resistor. So we are exploring another method of still getting IT. You can get IT using by adding the individual currents of that's flowing through each resistor, or you can also get total current by first of all evaluating the total resistance or the equivalent resistance RT, and then from there you now apply Ohm's law. Now remember from Ohm's law that I equal to V over R. The V will be VT over RT. You're looking for IT, so the voltage will be VT and the current and the resistance will be RT. From Ohm's law, V equals IR. Make I submit the formula. I will now be V over R. That's VT over RT. So where VT is total voltage and then the RT is total resistance. So now VT is 10 volts. That's the total voltage supplied by the voltage source. So that's 10 volts divided by RT. RT is 2000 divided by 7. 2000 over 7 ohms. That is our RT. We just obtained that right now. So we can say 10 divided by 2000 divided by 7. This would be wrong. It will be wrong. Yeah, this is very wrong. The calculator didn't follow the right BODMAS principle. So we have to, whoever doesn't know BODMAS, we have to be the one to arrange to the arrangement ourselves. We have to apply. So that 10 multiplied by 7 divided by 2000. That is the right way to do it, because the 1 over 7 will go up and now multiply the 10. That makes it 70 over 2000. So that's 0.035 amps. So we see here that the current we got from this formula is the same thing as this current. So these are the two ways you can obtain your total current. You either get the individual current flowing through the resistors and add those individual currents together in order to get your total current, or you get the total resistance of the whole circuit RT and then use Ohm's law to get your IT. So you can get IT, which is the total current, using two different approaches. If you examine those two approaches, either you sum the individual currents in the circuit, or you find the total resistance and use Ohm's law. So let's go. Obtaining the power consumed the power consumed by individual resistors. The power consumed by individual resistors in a parallel configuration. So for parallel configuration, for parallel connection of resistors, we've examined how to get the voltages across each resistor. We've examined how to get the current through each resistor in a parallel configuration. Now what is left is for us to get the power consumed. How much power is consumed by each resistor in a parallel configuration? So to do that, we just add a voltmeter across each resistor. Add a voltmeter across each resistor. Now you can either connect it this way at this point, or you can connect it closer to. It's all the same. The 2 points are the same. We need to shift this voltmeter backwards a bit so we can see the value. We need to adjust the circuit a bit, drag it forward a bit to optimize space, drag the voltmeter back a bit. So remember that the formula for power, like we examined during the last module. Okay, we still need space. We still need to shift the voltmeter backwards a bit. Remember the formula for power. The formula for power consumed by a load is IV. That is P equal to IV. P is equal to IV. So what it means is that for each resistor, you need to know the current through that resistor, and you need to know the voltage across that resistor. So that means to calculate the power consumed by R2, you need I2 and V2. So for each resistor, you need the current and the voltage. That's why after we've already connected an ammeter through each resistor to determine the current through each of those resistors. Now we want to connect the voltmeter across each resistor also. So to obtain the power consumed by each resistor, we connect both the ammeter through the resistor and a voltmeter across it. So we do both in order to get the power consumed by that resistor, because power P equals to IV. Okay. So let's connect this. Click, run. Okay, good. So we're left with let's shift this a bit, run. Still too close. Stop the simulation, and we need one more voltmeter for R4, the last resistor. Connect it. Click, run. Okay, good. So now we've connected 3 voltmeters across each resistor. So we have 3 resistors connected in parallel. Let's shift this ammeter closer a bit and shift this voltmeter closer a bit. Okay, and shift this that way. Okay, like so, and run. So we see here now that we have the voltages across each resistor is the same, 10 volt, 10 volt. Even though there's an ammeter connected in series with the resistors, it doesn't affect the voltage. So that means that the formula we proved, the parallel formula, is correct. Now let's measure that. The current is also the same because we've done that before. Let's copy our current formulas or the evaluations of our current. We got our current before. We got I2, we got I3, we got I4. So I2 is 0.02, I3 is 0. Oh, okay. I think I made a mistake here. I didn't remember to change it to 3. Let me adjust it now. This should be I3. Sorry, I left the I2 should be I3, and this should be I4, not I2. That is one of the issues you have when you try to duplicate in order to edit. You might forget to edit after duplicating. So we've determined before, we've evaluated before that I2 is 0.02 amps, I3 is 0.01 amp, and I4. Okay, let me go back and edit it here. So in case I make reference to this old one, I4, good. So I2 here, I3 shifted up here, I4 shifted up over there. Okay, so I2, I3, I4. So we have I2, we have I3, we have, and of course we verified that it's correct from live wire. Remember that P equals IV. Now we want to get the power consumed by each resistor. We verify that P equals IV is power equals to voltage times current. So P2, which is the power consumed by resistor R2, is now I2 multiplied by V2. Now the power consumed by this particular resistor in this line, and the current here, the R2 is here, this is R2. The current through R2 is 19.99 milliamps, which is about 20 milliamps, which is 0.02 amps, which is equal to 0.02 amps. That is the current multiplied by V2, which is 10 volts. 0.02 amps multiplied by 10 volts. That's P2. That's 0.02 multiplied by 10. That should give us 0.2 watts. Capital W, actually. Watts is the same, it's the name of a person, of a scientist. So the W will be capital, is the name of a person, not small w, it's capital W. So we've done that for P2. That's the power consumed by resistor R2. Let's go for P3, the power consumed by resistor R3. So P3 equals to I3 multiplied by V3. I3 is the current through R3, which is I3, is 10 milliamps. If you check here, that is 10 milliamps is flowing through R3. So 10 milliamps is 0.01 amp. We've proven that before. 0.01 amperes multiplied by the voltage across is 10 volts. We've proven that before, that the voltages across resistors in parallel is always the same. So it's still 10 volts. So that is 0.1 watts, capital W. So let's go for P4. P4 is the power consumed by the resistor R4, the last resistor, the third resistor, P4. So let's go for P4. P4 will be equal to I4 multiplied by V4. I4 multiplied by V4. I4 multiplied by V4. So I4 is 0.01. Sorry, I4 is 0.005, which is 5 milliamperes multiplied by 10 volts, which equal to 0.05 watts, capital W. So we've gotten the power consumed by the three resistors in parallel. So P2 consumes 0.2 watts, P3 consumes 0.1 watts, and P4 consumes 0.05 watts. So the power consumed by each resistor has been determined. So we've determined the power consumed by each resistor. So what is left now is total power, PT. What is total power consumed by all three resistors? PT equals to P2 plus P3 plus P4. So the power consumed by a circuit is just by all the loads or resistors in the circuit is simply the addition of all the individual power consumed by the resistor. So that's 0.2 watts plus 0.1 watts plus 0.05 watts. So if you had the power consumed by each resistor in a circuit, you obtain the total power consumed by all the resistors or all the loads in a circuit. So like I said before, that a load cannot, it's not compulsory that a load has to be a resistor. It can also be a bulb, it can be an LED. So the power consumed by all the resistors or all the loads in a circuit is just simply the addition of the individual power consumed. So 0.2 plus 0.1 plus 0.05, which is 0.35 watts. So 0.35 watts is the total power consumed by all the resistors in the circuit. So where PT equals to total power consumed. Total power consumed. total power consumed by all the resistors loads. So total power consumed by all the resistors is 0.35 watts. Like I said before, resistors are loads, and a load can be a resistor, a load can be a capacitor, a load can be a bulb, an LED. So but for illustration purposes, we are using resistor as our load. So it could as well be in a bulb. I could have as well used 3 bulbs in parallel instead of 3 resistors. So now, alternatively, we can also get total power. There's another way we can get total power apart from adding the individual power. Apart from adding the individual power consumed by each resistor, we can get total power by doing total power equal to total current multiplied by total voltage. That is still using the P equals to IV, but this time around the I is total I and the V is total V, where the I is total current, which is 0.035 amps. We've gotten that before. Total current is 0.035 amps. We've obtained that before. Multiplied by total voltage, which is 10 volts. So this is another way of getting total power. Apart from adding the individual power supplies, power consumed together, we can get total power by just multiplying total current by total voltage, which is 0.35 watts. So here that it's the same thing. If whether we use this formula or we had the individual power consumed by each load or each resistor, the result is the same. Total power is the same. PT using the addition of individual power is 0.35 watts, and using PT equals to IT times VT still gave us the 0.35 watts. So it's all the same. So we got the voltages across individual resistors in a parallel configuration. Now we are done with we've spoken extensively on parallel configuration. Let's go through series. So the current through individual resistors in a series configuration. So we've done for voltages across resistor configurations in parallel or in a parallel resistor configuration. We've done that already. So let's go through series configuration. If you connect resistors in series, what is the current flowing through in the individual resistors? So we'll be switching over from resistors in parallel. Now we're going to go to series. We spent a lot of time on resistors in parallel. I hope by now you really fully grasp the concept of connecting loads in parallel and how you get the individual power, the individual voltages, and the individual currents through, across, or consumed by each of those individual resistors in a parallel configuration. So let's go back to live wire, get a resistor, flip it or rotate it, and then rotate it to the right, rotate it again. We have R1 and R2. We have R1 and R2. R1, R2. Power supply. 10 volts, 9 volts. After when I'm done, 9 volts. Connect 9 volts battery. We are connecting the 9 volt battery across 2 resistors in series. We've done this before. We're expanding on that a bit. So let's get an ammeter. Now we want to measure the current through each resistor in series. That means that we will need an ammeter for each resistor. We have 2 resistors in series. We want to determine the current through each of those resistors. So it means that we will need 2 ammeters, 1 ammeter for each resistor. So let's shift the resistors back a bit. Connect ammeter 1 through in series or through in series with R1. Delete this wire, shift R2 backwards a bit, then connect ammeter 2 in series with R2. So with these two ammeters, we'll be able to measure the current through R1 and the current through R2, and be able to determine the differences between, or the difference in the current flowing through R1 and the current flowing through R2, R1 and R2. So let's see how different the two currents will be, the current through R1 and the current through R2. Double click, let's change the value of R1 to, let's change the value to 500 ohms. So R1 is 500 ohms, and let's change R2 to 1000 ohms. So let's see, would they draw two different currents, as in with the value of the current change? Let's change the voltage to 10 volts. With the value of the current for R1 change to the value of current for R2, will it change? Let's see. Simulate, run, click. Let's simulate. No, the answer is no. Even though the resistors are different, the current is exactly the same. It's the same current flowing through R1 and R2. Even though the resistances are the same, the current is exactly the same. So that's 6.6 milliamps. 6.6 milliamps was flowing through both resistors, even though both resistors were at different value. One resistor was 500 ohms, the other one was 1000 ohms. The same current, which is 6.6 milliamps, flowed through both resistors. So if I delete the second ammeter, click and look at that, that's 6.6 milliamps flowing through. So at the end of the day, I really did not need to use two ammeters. Only one ammeter will suffice, because the same current is flowing through them. Having two ammeters is just repetition. It's the same current that flows through the two resistors. So just having only one ammeter at one end is okay. That's 6.6 milliamps, because even when I had two ammeters, both of them read the same value, 6.6 milliamps. So regardless of the value of the resistance, if you connect resistors in series, the same current will flow through them. That is another hypothesis I want you to take to heart or to store in your mind. So if I had one more resistor in series, let's make it 3 resistors in series. Click and drag, click and drag, click and delete. So I want to add one more resistor in series, and remember that I said as long as you connect terminals right, regardless of whether it's vertical or horizontal, if you connect the right terminals, it will still be in series. So for nomenclature's sake, let me call this one R4. Okay, this R4 already. R6. Let's call this one maybe R7 or something. R5 has been taken. R7. Let me call this R3. So R1, R2, R3. So if I have R1, R2, R3, and let's say R3 is 2000 ohms, 2000 ohms. Okay. So R1, R2, R3. Let me shift R3 down a bit. Let me complete the circuit. Click and drag. Click, drag. Click, delete. Let me get one more ammeter, so that each of the 3 resistors will have their own ammeter. So R3 has its own ammeter to measure the current flowing through just R3 alone. So if normally, logically speaking, if you want to measure current through 3 resistors, you normally need 3 ammeters, each ammeter to measure current through each resistor. So each resistor gets its own ammeter. Normal, that's logically speaking, but that's, we will see later on that is a waste. So click, drag. So each ammeter connected to each resistor in series, R1, R2, R3 in series. We connected an ammeter in series with each resistor to measure the current through each individual resistor. So click and delete, click. So let's for our second circuit, let's also make it 3 resistors in series. I duplicated the 2000 ohm resistor, which is R3. I duplicated it, and let me complete the circuit. Click, drag, click, connect. So let's see, let's simulate. Let me make this V1, right? Can I make it V1? V1, okay. That's just for nomenclature's sake. Actually, it doesn't, whether we use B or V, it doesn't matter. V2, just for the sake of nomenclature. And simulate. Let's simulate. So we see that the current here it has dropped now to 2 point. I can't see this clearly. 2 point something volts. 2 point, sorry, milliamps. Maybe 2.9, maybe 2.9 or 2.86 milliamps. So now the same current, 2.86, 2.86, 2.86. So it's the same current flowing through all three resistors. Even when the second circuit, I use just one ammeter, is the same thing. So there was no need for us to get 3 ammeters. If you want to measure current through resistors in series, just one ammeter will suffice, because the same current flows through resistors in series. So although the value dropped from 6.67 to about 2.86 something, the same current still flowed. If the value of the current would drop, it will drop for everybody, for all the resistors in series. So now another hypothesis I want you to note is that the current through resistors connected in series is the same. Just the same way the voltage across resistors in parallel is the same. Now, for parallel resistors, it is voltage that is constant. Voltage is the same. For series resistors, it is current that is the same. So see that there's a kind of inverse relationship between resistors in parallel and resistors in series. If you are working with resistors that are in series, the current is the same. If you are working with resistors that are in parallel, the voltage is the same. So I want you to keep these two hypotheses, these two theories, keep it to heart. It will basically control. It's a basic law that you apply to any circuit you want to simplify. If you want to work on any circuit, you must always remember that if the resistors or the loads are in parallel, that the voltage is the same across all the loads or across all the resistors that are connected in parallel. And if the resistors or the loads are connected in series, that it is current that is the same. So for resistors in series, the current is the same. For resistors in parallel, the voltage is the same. So make sure, if you don't remember any other thing after this course, make sure you remember these two theories. They are very, very important. You are going to apply them throughout any you are going to apply them to any circuit, any electronic circuit you come across in the future. You are definitely going to apply these two theories. It's very important. So in other words, IT, which is total current, equal to I1 equal to I2 equal to I3. So the total current that flows through resistors in series, that total current is the same thing as the individual current. Remember that when we were working with resistors in parallel, that the total voltage, which was 10 volts, was the same thing as the individual voltage. Remember that V1 was equal to 10 volts, V2 was 10 volts, V3 was 10 volts, V4 was 10 volts, and total voltage was still 10 volts. That was for parallel. But for series, the total current is IT. I1 is IT, I2 is IT, I3 is IT. All the individual currents through each resistor equal to the total current supplied by the voltage source or the power source. So we can get IT by also using the Ohm's law. Remember that V equals to IR. So it means that I will be equal to V over T. So you can get IT by dividing VT by RT. So RT, how do we get RT? How do you get total resistance? Remember that for series resistors, that total resistance RT equal to R1 plus R2 plus R. Just add them together. If they are in series, just add all the resistors together directly. So the R1 is I think it's R1 is 500 ohms, R2 is 1000 ohms, and R3 is 2000 ohms. So which equal to, if you add all three together, you will get 3500 ohms. So these three resistors in series, 500 ohm resistor, 1000 ohm resistor, 2000, if you add them in series, you get 3500 ohms. So that it means that the total resistance of these three resistors in series is 3500 ohms. So RT equal to 3500. What about VT? VT is total voltage. VT is 10 volts. That is the voltage of the voltage source or the battery power supply. So that's 10 volts, which is VT, divided by 3500 ohms, which is RT. VT is 10 volts, RT is 3500 ohms. So that's 10 volts divided by 3500, which is equal to 0.0028 or 0.00286 amps. 0.00286 or 2857 amperes. Or let's make it 286 amperes, capital A. So we can simplify that. That will be 2.86 milliamperes. 2.86 milliamperes. That is total current IT. I remember that when we simulate, we got this 2.86. So we got 2.86 milliamperes current flowing. By calculation, we got this by calculation. When we ran the experiment, we still got the same 2.86 milliamp, and that same 2.86 milliamps is what is flowing through I1. It's the same 2.86 milliamp that is flowing through I2. It's the same 2.86 milliamp that is flowing through I3. So the current through I1, I2, I3, they are the same as the total current. Why? Because all the resistors are connected in series. If the resistors are connected in parallel, the current will not be the same. So if you connect resistors in series, regardless of the values, the individual values of the resistors, regardless of the individual resistance value of the resistors, the current flowing through all of them will be exactly the same. So since I1 IT equal to I1 equals to I2 equals to I3, it means that I1 on its own, I1 is 2.86. I2 is also equal to 2.86 milliamps. Automatically, of course, that means that I3 is also equal to 2.86 milliamps. So you've seen here that with all these, the individual ammeters that we connected to the through each resistor, the currents are the same. So if you have resistors in series and you want to measure the current, you don't need up to 3. You just need only one. You only need only one ammeter. You don't need 3 or more ammeters. Just one ammeter will measure the same current through all the resistors. So let's go to determination of voltage across resistors connected in series. So we've determined that the current through resistors, through the individual resistors, when those resistors are connected in series, that the current through them is the same. Now what about the voltage? Is the voltage the same for series resistor? Let's confirm. If you connect resistors in series, would the voltages be the same? Would the voltages across each resistor be the same if you connect them in series? Let's confirm whether that is true. But we've confirmed already that the current through each of those resistors that are connected in series, the current through them is the same. We've confirmed that. I want to confirm what happens to the voltage when you connect the resistors in series. Would the individual voltages across each resistor connected in series, would those individual voltages, would they be the same or would they be different based on the value of the resistance of the individual resistors? Let's confirm that. So we are back in live wire, R2, R3 and R4. So R2, R3, R4, they are connected in series. Like I said, there are a couple of ways you can connect resistors in series. As long as the right terminals are connected to each other, the orientation of the resistor or the resistors don't matter. So let's track this down a bit. So I will still have one, like I said before, or we said just now, that if you want to measure current through resistors that are connected in series, you only need one ammeter. Just one ammeter is okay. So one ammeter is okay to measure the current through all these resistors. Need to be the same current. If we've confirmed that, to be the same current flowing through all the two resistors. Now we want to measure the voltages across each individual resistor. So we want to see whether these voltages should be the same. So let's rotate the voltmeter. Click, click, and click, click, and click, and click again. Rotate, click, and click, and It's misbehaving. Let me delete, start again. Click and click, click and click. Then the last resistor, let me drag it up a bit. That changes the shape. Let me delete this cable. Delete the cable, redraw the cable, connect, click, draw the cable downwards. Okay, so let me connect this voltmeter across, shift it a bit, shift it backwards a bit, click and click, click and click. So I've connected 3 voltmeters across each individual resistor, where the resistors are connected together in series and not in parallel. So let me adjust this cable. I can also, if I connect it like it's the same thing, because there's no difference between the 2 connection points. There's no difference. So I can connect it this way, or I can connect it the way I previously connected it. So let's run an experiment. Now we see here that the voltages are different. So the same current flows through all 3 resistors. We've confirmed that before. Before we run simulation, let's do the calculation. Let's see whether you can determine by calculation, you can determine the voltages across each resistor. Let's determine it by calculation, then we'll verify it using live wire. So V2 equal to I2 times R2 from Ohm's law. Remember from Ohm's law that V equals IR. So if you want to get V2, V2 will be I2 multiplied by R2. Let's change the font to Times New Roman. Times New Roman, it's probably, that's a better way of representing text. At least, I won't say better, probably a more familiar way of representing text. So I2 multiplied by V2. Sorry, by R2 rather, sorry. V2 equals to I2 times R2. That's Ohm's law. So let's copy this. Copy and paste. Drag it up a bit, align it at the top. So we see here that I2 is 2.86 milliamps. We've determined that I2, I3 and I4 are the same. I2, I3 and I4. Before I used I1, I2, I3. Now since I've changed the resistors to R2, R3, it's just nomenclature, just renaming basically. So I2, all the currents basically they are the same. So 2.86 milliamps is 0.00286. So multiply by R2. What is R2? R2 is 500 ohms. 500 ohms, which is equal to, let's get a calculator out. Search for calculator. Open it up. That's 0.00286 multiplied by 500. That's equal to 1.43. That's 1.43 volts. 1.43 volts. Which means volts, not amperes. Voltage. Volts for voltage. 1.43 volts. Yeah, that should work. 1.43 volts. Let's align that. So the voltage across V2, we got it by multiplying the current through R2, which is I2, multiplied by the resistance of that R2, which is 500. So let's go for R3. Sorry, V3. V3 will be I3 multiplied by R3. So the voltage across resistor R3 is I3 multiplied by R3. Now remember that I3 is the same current as I2, same current as IT, total current, they are all the same. So that's 0.00286 amps multiplied by R3 is 1000 ohms, which will be equal to, should be around 2.86 volts if I'm right. That should be 2.86 volts. Equal to 2.86. Okay, let's just verify this calculator here, but it should be 2.86, all things being equal. 0.00286 multiplied by 1000, 0, another 0, equal to 2.86. That's 2.86 volts. Space 2.86 volts. 2.86 volts. So that is V3. let's go for V4. So we are already seeing that V2 and V3 are different. So let's see whether V4 will also be different or will be the same. So V4 equal to I4 multiplied by R4, which is equal to this particular current, still the same current as you've proven before, 0. Okay, I've done copy and paste. Let me just double click. Copy just the current alone. I4 multiplied by R4 is 2000 ohms, which is equal to, let's get our calculator out, and that will be 0.00286 multiplied by 2000 ohms, 2000 ohms, which is 5.72 volts. 5.72 volts equal to 5.72 volts. Good. So that's the voltage. That's the voltage across R4. So we see here that the voltages across R2, R3, and R4, they are different voltages. Even though the currents through the resistors in series are the same, the voltages are not the same. The currents are the same, but the voltages are not the same. Let's run an experiment now. Look at this. 1.43 is the same. This is 1.43 here. That's 1.4. It matches. 1.43 matches. Here, this is 2.86. If I can see that well. Now this is 2.86, the same voltage. This is 5.72, the same voltage. And the current here is 2.86 milliamps. The same current. That's the same current. That's this current here, 0.00286. So the same current flows through, but the voltages across each individual resistor is different. So for series resistors, or for resistors in series, the voltages across each resistor is different, but the current through them is the same. And we've proven that already by by calculating for the individual voltages. We proved this by also running a virtual experiment on LiveWire virtual laboratory. We also proved it. So I hope that I hope you've grasped this concept. The concept that for resistors in series, current is the same, but voltages differ based on the resistances of the resistors. So in a series resistor configuration, the total voltage basically is the sum of the individual voltages. So remember that for parallel, for when we were discussing parallel, for parallel configuration, the total current was the sum of the individual currents. That's for parallel, and the voltage was the same. That's for parallel. But for series, the current is the same, the total voltage is the sum of individual voltages. So in a series resistor configuration, the total voltage of the circuit is the sum of the voltages across the individual resistors. So if I want to get the total voltage of this circuit, I'll have to add the individual voltages V2, V3, and V4. So VT is total voltage. VT, or we can call it V1. In this case, we can call it V1 or VT. Let's stick to VT. VT equal to V2 plus V3 plus V4. And that gives us V2 is 1.43 volts plus 2.86 volts, which is V3, plus V4, which is 5.72 volts, if I'm right. 5.72 volts. So that's VT, that's total voltage. So let's add them together. 5.72 volts plus 2.86 volts plus 1.43 volts. Straight off, that's 10.01 volts, equal to 10.01 volts.
So approximately it's 10 volt basically. It's basically 10. Now remember, look at this. This is 10 volt here. This is a 10 volt battery. So we are able to get back the original voltage source of 10 volts by adding the individual voltages across the resistors in series. So the total 10 volts, when you supply a voltage source, when you supply a voltage from a voltage source, when you supply it to resistors in series, the voltages will be shared by all the resistors will take their own parts. So at the end of the day, if you had the individual resistors, if you had the individual voltages of the resistors, if you had it together, you will get the original voltage you applied. You will get the voltage source. So now let's go determine the power consumed by individual resistors in series, and we'll continue from there next time. So we will stop here for now for this module, and in the fourth module we would talk about power, the power consumed by individual resistors in a series configuration. So I hope you understand what we've gone through so far. Thank you.